No, eso
y se ellos
y luego
Oh, I should have a Kelsey here. I should have a watch to oh yeah,
They thought about that.
yeah, you can all put it
pero lo que me dice es how do you dine?
Good night.
A mí me pasa lo mismo, tarda un poquito.
Vale, son las 2. Las 2. ¿Cuál hablo primero? O sea que tienes un...
Esos dos son. Ahí va. Correcto.
Sería en blanco. Tenemos un problema
Que negro se ve. Se apagará alguna luz para los líneas.
La gente
Se nos va a ver a nosotros y se nos va a oír.
se os va a ver si la cámara o no. Hay ratos que se ve bien.
Hay rato que se ve bien.
Pero es que no se puede definir cuándo. ¿Ves cómo sí que se ve el título bien? A ver, bien. Estamos en ello. Está la cámara ahí. ¿Ves cómo sí que se... Ahora lo intenta enfocar. A ver si me cogen aquí. Estaba pensando que a ver si es que cuando enfoca la persona que se enfoca lo de acá, pues no sé qué se ve. Estoy ajustando. Vale, sí que hay una cosa, tanto para Juan como para...
Juan.
La cámara os va a seguir, con lo que si os venís aquí, os va a enfocar aquí y no va a enfocar a esto. Porque la cámara automáticamente...
O sea, su idea sería ponernos a la derecha de...
Poneros cerca de lo que es la presentación para que la presentación...
Vamos a tener mando para pasar, ¿verdad?
Sí, mira. Para por ahí. Vale, sí que se ve, pero se ve Se ve así.
Blanquito, ¿no? Has dicho, ¿no?
No se ve tan bien como debería.
Oye, a mí tengo un montón de tú te puedes poner aquí, lo marcas ahí.
No, porque, vale,
No
bueno,
es la mejor calidad, pero se ve algo. En el de Sheldon se veía peor. En este se ve.
¿pero se veía peor?
¿Qué tal, Oscar? ¿Qué tal?
Pero que digo, que no va a haber, que se va a hacer todo bien. ¿Vale? Vale.
En vuestra charla vamos a quitar el seguir y empezar más la presentación.
Mejor.
Sí, ya está. Ya podemos empezar.
No, no ha habido tiempo. Sí,
¿Cuánto? Alex, Pablo. Es cierto, pues no maricona, que está pagado. Apagado significa encendido significa apagado. Okay. Good morning to everybody. I have been told to speak in English, but I believe in my case there is no difference between English and Spanish. Okay. Thanks to everybody that comes here, live or online, to this mini workshop that will be up with Perenflo giving his talk, but before that we have two short talks. The first one by Gustavo Muñoz from the University Complutense University of Valencia, of Madrid. And he is going to speak about one of his area of expertise, which is geometry of Banach spaces, particularly finite dimensional geometry of finite dimensional spaces, or in this case, apparently, is infinite dimensional setting. But one important thing is that people that is online, our great Sheldon Dantas is taking care of all the questions that you have, and at the very end, you can write a question, and at the very end of the talk of each of the talk, the question will be asked by him, and then the corresponding speaker will try to answer. And then, well, if not, Gustavo is going to speak about product or normal product polynomial, and then please, Gustavo.
Okay, thank you very much for the introduction. Before I begin my talk, I would like to thank both Manuel and Domingo for their kind invitation to this workshop, which is really a historical event in functional analysis, because we are about to witness how Professor Enzo presents for the first time in Spain his solution to the invariant subspace problem for Hilbert spaces. So the title of my talk is Norms of Products of Polynomials. I would have chosen this alternative title for the talk, which is the factor problem for polynomials. That can be stated in its more general formulation as follows. We start with three different polynomial spaces endowed with three different norms. And then what we have to do is to find the best estimates, lambda and mu, in these three inequalities, where we are trying to find lower and upper bounds on the norm of the product of two polynomials in terms of the product of the norms of the factors. Okay. This problem appears many times many times in functional analysis. And what I'm going to do during the next 20 minutes or so is to present some situations where this problem appears from the most general case in polynomials of Banach spaces to polynomials in the real line or the complex plane in just one variable. I will also mention the connection of this problem with the invariance of space problem for Banach spaces, which was solved by Professor Enflo in 1997. Let me begin first by the most general case, which is the case of polynomials in a general Banach space, for which I will be using the conventional notations. We will work all the time with scalar valued polynomials, both homogeneous or not, okay? And they will be all the time bounded polynomials so that we can define the conventional norm in spaces of polynomials in Banach spaces as the supreme norm over the unit pole. Okay, in this setting, it is quite obvious that the norm of the product must be less than or equal than the product of the norms. And that would happen even if we don't consider polynomials. That happens for any choice of functions. So the interesting problem in this case would be this one. Is there a constant for a specific Banach space such that this inequality holds for any choice of P and Q being polynomials of degree at most n and polynomials of degree at most k, respectively? That constant will depend naturally on n, k, and the Banach space. It was proved by Ryan and Tourette in the 90s that there is a universal constant that fits here for any Banach spaces, which depends only on n and k. But they didn't provide a sharp bound on the constant. Here we can find one proved by Benitez and Antopoulos and Tong in 1998, where they prove, at least for the complex case, that the constant must be less than or equal to n plus k to the power n plus k divided by n to the n times k to the k. And this estimate is optimal in the sense that equality is achieved for the complex level one. And by the way, for these two polynomials. Observe that the polynomials are homogeneous, and therefore this constant is also optimal for homogeneous polynomials. In the real case, where polynomials on a real Banach space, we encounter a much different constant. In a joint paper with Gustavo Araujo, Enflo, Daniel Rodriguez, and Juan Sebane, published in, I think it is wrong, it is 2020, it was proved that the constant for the real case is this strange number here, which is closely related to the roots of the Chebyshev polynomial of the second kind of degree m, which is defined, I didn't put it down here, it is defined as cosine of n times r cosine of x, at least for x between -1 and 1. Okay, the proof of this result, well, I'm not going to provide any proof in this talk, but the proof relies very much on the corresponding result for polynomials in the real line, which was proved by Gorwin and Erdelji in the 90s. Well, we can also state the factor problem for polynomials considering only homogeneous polynomials. In that case, we may obtain here a different constant from the constant that holds for all polynomials. And indeed, that is true. For instance, Pinasco in 2012 proved that the constant for complex Hilbert cases turns out to be the square root of the constant that holds for general Banach spaces. This result can be improved, and it was done by Carando, Pinasco, and Rodriguez 1 year later for big LP spaces, at least for P between -1 and 1. They proved that the constant in this case is exactly the constant that holds for general Banach spaces raised to the power 1/p. Well, here we have one more situation in which the factor problem appears for polynomials in Banach spaces. Suppose that the factors are linear functionals. And in that case, the base constant here is called the linear polarization constant. So it provides a sharp bound on the product of the norms of the factors in terms of the norm of the product. Well, there exists, at least for both real and complex Banach spaces, there exists a universal constant which depends only on the degree of the polynomial, and that constant turns out to be m to the m, and equality is achieved for L1 spaces, both real and complex. The proof for the real case was done by Reves and Sarantopoulos in 2004, and previously, in 1988, Benitez, Santopoulos, and Tong proved it for the complex case. Well, there have been a lot of results done in order to calculate linear polarization constants of Banach spaces. Not only that, they have also tried to prove certain properties of linear polarization constants. But above all the problems that have been done on this topic, I would like to underline this one, which is nothing but the calculation of the linear polarization constants of Hilbert spaces. Actually, the problem was solved, at least for the complex case, by Arias de Reina in 1998, when he proved that for a complex Hilbert space, well, we have to admit this extra hypothesis. It has to be of dimension, at least n. The linear polarization constant of this space is exactly m to the power m/2. By the way, equality is attained for products of linear forms of this kind. This scalar product of AK, which is fixed, times x, and a set of n linear functionals of this type provides equality in the factor problem if the set of the AKs is an orthonormal set. Okay, this question has been stated also for the real case, but no proof has been done so far. It has been conjectured that the same constant holds for real Hilbert spaces, but up to date, and to my knowledge, there is no proof of this. However, some progress has been done during the last 25 years. For instance, I mentioned just a few results. Benitez, Sarantopoulos, and Tong proved it, at least for m up to 5. Pinasco proved it for m less than or equal to 14. And here you are two estimates, which in my opinion and to my knowledge are among the best. Okay, that's all I wanted to say about the factor problem for polynomials in general Banach spaces. If you consider polynomials in a finite number of variables or even polynomials in just one variable, real or complex, with real or complex coefficients, or even infinite series, you can state the same problems we have seen so far, and additionally, some others, using many different norms, different from the usual norm for Banach spaces. Here you have a list of conventional, of common choices for the norms in the factor problem for polynomials in a finite number of variables. Could be using the subnorm over the unit interval in the real line, or the unit disk in the complex plane, or a LP-like norm, big LP-like norms, or little LP norms of the coefficients, like unary norms or Bombieri LP norms. Well, I'm going to define all this in the next slide. Let us consider a polynomial with its coefficients in the usual basis of polynomials in a finite number of variables. Then the LP norm of its coefficients will be defined in a natural way as in 1 and 2. Okay, we could also be considering this modification of the LP norm of the coefficients, also called sometimes Bombieri LP norm. Sometimes it is also used this big LP kind norm, which involves integrals, and the classical subnorm over the unit wall of L infinity or the unit polydisk. So the thing now is to estimate the test constants lambda and mu in these two inequalities using several combinations of the norms I have listed here. Okay? Let us see what kind of results we have. Well, I present first this result by Enflow that dates back to 1988. I will explain why in a minute. But to understand it, we have to define what concentration means. We say that a polynomial of degree at most n in capital N variables has concentration d, is a factor between 0 and 1, at degree k, if the L1 norm of the coefficients of p associated to degrees less than k dominates over the whole L1 norm of the polynomial, the coefficients of the polynomial up to a factor d. Having this in mind, Enflow proved in 1987 that for any choice of the constants d1, d2, and 1k, n prime, k prime, there exists a constant depending only on those parameters, such that for every polynomial of degree at most n in capital N variables, in fact, we can omit the number of variables because the final result does not depend at all in the number of variables, with concentration d1 at degree n prime, and for every polynomial q of degree at most k, with concentration d2 at degree k prime, we have that the L1 norm of the coefficients of the product of p and q is bounded below by lambda times the product of the L1 norms of the factors p and q. The important thing about this result is that the constant lambda does not depend at all on the number of variables, not even on the degree of the polynomials. This result is important because Professor Enflow used it several times in the solution of the invariant space problem for Banach spaces, published in his famous paper in Acta Mathematica in 1987, of which this is the first page. Okay, if in the previous result you drop the condition on concentration and you consider only homogeneous polynomials, then it can be proved that there exists a constant that depends only on n and k, such that for every n homogeneous polynomial and every k homogeneous polynomial, the L1 norm of the coefficients of the product p and q is bounded below by lambda times the product of the L1 norm of the factors p and q. Here I present another result, which was published in 1990 in a paper that contained lots of bounds like this, by Bosami, Bombieri, Enflow, and Montgomery. In these two inequalities, we have first an upper bound for the LP norm of the coefficients of the product of two homogeneous polynomials in terms of the product of their LP norms of the coefficients. And in the second, we find a lower estimate, which by the way is sharp, on the product of the Bombieri LP norm of P times Q in terms of the product of the Bombieri LP norms of the factors. Again, to finish, I will present another result which appears in a joint paper with Gustavo Araujo, Enflow, Daniel Rodriguez, and Juan Sebane that appeared 2 or 3 years ago, where we work with lacunary norms, for which it will be necessary to define first lacunary sets. Well, this to me is quite difficult to grasp the concept, and it is defined by induction as follows. Lacunary sets are sets in the positive integers. We say that the set is zero lacunary if it is a singleton containing only one natural number. Okay. Now, if we have a set E of natural numbers, we say that it is k lacunary if E intersects its non-trivial translates in sets that are contained in a k-1 lacunary set. Okay. Okay, we denote with omega k the collection of all k lacunary subsets. This is needed to define the k lacunary norm of a polynomial. Now we are in the case of polynomials in just one variable. So in this case, h is has this form. These are its coefficients, and the k lacunary norm of h is defined as the supremum ranging over all k lacunary sets of the L1 norm of the coefficients of h restricted to E. Well, this is not the proper restriction. By h restricted to E, we mean the same polynomial where we have to remove all the coefficients whose index is not in E. Okay? Well, the k lacunary norms enjoy certain properties, and here we have at least two of them. They form an increasing sequence whose limit is the L1 norm of the coefficients. Okay. Well, using this, it was proved that for any choice of positive integers and any positive constant c and k, and any q bigger than 1, there exists a constant which depends on all those parameters, such that for every polynomials in one variable, h and q, satisfying a certain number of constraints or restrictions, the I lacunary norm of the product is bounded below by beta times the product of the L1 norm of the factors. Okay, and the constant does not depend on the degree of polynomials. Okay. And well, I think I have run out of time and I have run out of slides too, so thank you very much for your attention.
Thank you very much, Gustavo, for so nice and interesting talk. That is a lot in finite dimensional setting too.
Yeah.
And well, before asking question, I would like to apologize to people that are online because they say to us that YouTube almost is impossible to read what is written on the blackboard. But we realized 5 minutes before the talk, and then changes couldn't be done. But I have to say that parent talk will be on the blackboard, and then theoretically at least the people on YouTube could read perfectly what he's going to write. In the case of one, Joanne, you have prepared a Beamer, or are you going to write?
Beamer, yes.
But the Beamer will be on the website in 5 minutes.
Okay, and the Beamer will be put in the website in 5 minutes, and then
They
you
have
can
to
check.
refresh the website.
Good. But well, now it's the turn for the question. Any question or remark for the people present in the room? Any question online?
No questions.
Well, anyway, I would like to say that this is all these are beautiful, but because they are so natural and so surprising. But I am particularly surprised that you can control lacunary set, whatever any set that you can control with the product. It's, to me, has been a surprise. I should have known the paper, but I didn't know, and the results surprised me really.
Yes, thank you for the nice talk. When I can, since I worked on this type of things, also mainly for the purpose of using them for the invariant subspace problem in Banach spaces. This is, it turned out that the only one of these inequalities in the end was used. But there are certainly quite a few problems about the best constants which are not solved. Now, if we just restrict ourselves to one variable and the degrees of m and n, then the norm of the product is bounded from below by something that it goes down exponentially with m and n. But in some cases, we don't have, especially for when we only have concentration up to certain degrees. The best estimates today are that they go down double exponentially fast. And probably the truth is that it is exponential also in those cases, especially when it comes to, for instance, the largest coefficient in product of polynomials. The largest coefficient is, of course, smaller than the L1 or L2, little L2.
Mhm.
So I think there are quite a bit of open analysis problems in this direction.
Any other question or remark? If not, let's thank Gustavo again for his. We have 3 minutes for quantum paper.
Yeah, we have some poster.
Con la camisa roja.
No problem.
Okay. Well, in 1 minute, but the introduction will be done in such a way that we will. Okay, our next second speaker of the three is Juan Bionigno Giovanni Sepúlveda. He's again, in this case, for the University Complutense of Madrid, and he has worked in several areas. He is a former student of Richard Arrow, who is in some sense our uncle. And then mathematical uncle, and then he had working in several areas. Some paper with Gustavo in geometry of Banach spaces, a lot of things about linearization, other things even related with health, and many other areas. And he has many more than 160 pages, and very well situated, and with a lot of credits given. But he also in the last 20 years or 10 years has worked a lot with Perenflo, has many things to learn.
More or less.
More or less, yes. Well, you met him when you were a graduate student, and then when you met him in Kent. And then it's a very fortunate things for Juan, and I believe something a little bit also for her. And now he's going to speak about another joint paper, no, with parent, no, about Banach spaces having infinitely many zeros.
Thank you very much, Manolo. Well, I would like to thank everyone, either attending remotely online or attending here physically. Thank you very much, and thank you, Manolo, Javier, and Domingo for organizing this very nice workshop, and thank you to Per for coming here as well. Well, actually, my talk is more in the line. I mean, the purpose of my talk serves two different aims. First of all, to talk a little bit about other things that Per has done besides the famous problems he's famous for, because he's done many other things besides all those very hard problems he's been solving for the decades. And also a second aim that this humble talk serves is to congratulate Per on his achievements and on his very soon to be 80th anniversary. So to dedicate the lecture to him as well. And well, before talking about mathematics, I would like to do a very brief introduction on how I met Per, but I won't. I mean, probably that part will be much more interesting than the talk itself. The mathematics, I mean. Well, when I first met Per, it was in Kenya, as Manolo just said, 22 years ago. And when after that, every time someone mentioned Per, I always had this image in my mind where he's always smiling. He always has this huge smile, and throughout the years, this smile hasn't changed. You see, this was 22 years ago, and it was yesterday. So he holds. I mean, even though when we talk about mathematics, I many times have a very hard time following the speed of his reasoning. Well, unless you get the smile, which is nice to have when you're talking with a top-notch mathematician. And well, the aim of this small talk that I'm giving is essentially to talk about some results on this paper that appeared 8-9 years ago in Transactional Mathematical Society, together with the late Vladimir Gurari and with Per, related to a topic that we started studying at the beginning of 2003-2004, that it has to do with this word over here, spatiality. Essentially, it's a topic that I believe many of you present here know what it means. The idea behind this made-up word that was coined by Vladimir Gurari himself is the following. You have a set, okay, a subset of a topological vector space, of a just vector space. That we don't have to have a topology. We don't want to. A subset of elements of a vector space enjoying certain property. For example, you can consider the typical example of the set of continuous functions which are nowhere differentiable, like the typical Weierstrass monster. That set by itself does not have any kind of structure at all. It is in general not a vector space, it is not an algebra, it is not a Banach space, or whatever. But we will say that the set we're considering is lineable if that set, together with the zero, has inside an infinite dimensional linear space. And we will say that this is special if that linear space can be chosen to be closed. Okay, just two definitions that many of us are familiar with. And the idea is to talk about some results on this area that is with Per. But before that, I would like to introduce this problem with two other examples before the main one that with Professor Enflo, mainly because at some point when we started working on this lineability property, it came out that many of the sets were considered like continuous or differentiable functions or differentiable nowhere monotone functions, or whichever function you can imagine, no matter how pathological that is, if you consider the set of elements enjoying that strange property, at the end, everything seemed to be linear. So we could find infinite dimensional linear spaces, except for 0, of almost everything you could imagine, no matter how pathological the property is. Well, at some point, the interesting thing was to try to find examples that were not linear, but non-trivial examples. So this is what I would like to focus on today, to show a couple of examples of very easy to understand properties that are very intuitive, but on the other hand, we cannot find infinite dimensional spaces of such elements. A first one is something that we did some while ago. It's called a property to be Sierpinski-Sigmund function. The origin of this notion dates back to a theorem by Henry Blumberg from 100 years ago, that it was kind of counterintuitive, but to me it's very surprising that if we have any function from R to R, any one variable function, there's always exists a then subset S in R, such that the function f restricted to S is continuous. No matter how strange the function you think of, whichever function you think of, you can always have a then subset in R, so that when you restrict the function to S, the function is continuous. Okay? So then, after examining the proof of the original proof of Blumberg, the proof shows that this set S that exists is actually countable. So one can think of the following. Can we choose the S in Blumberg's theorem to be uncountable? So how large can that set S be so that the property is enjoyed? Well, just a year afterwards, Sierpinski and Sigmund showed that there exists one function such that for any subset Z of R of cardinality continuum, the restriction is not continuous. So they answered the question, and then, well, now we have here an example of a function f enjoying a pathological property. That the pathological property is that whatever set of cardinality continuum you have, the restriction of the function is not continuous. So then the natural question at that point was to wonder how many of these functions can we get? Okay, and the how many means can we have a linear space of functions like those, except for 0. The 0 has always need to be, because otherwise we don't have a vector space. And well, we work a bit around this, and essentially we started getting positive results. If we denote by SZ of R to the functions enjoying the previous property, then in 2010 it was shown that this set contains an infinite dimensional vector space of dimension some cardinal number between the continuum but less than or equal to the power of the continuum. This 2 to the C would be the optimal solution, because we cannot go higher. Okay, the dimension of R to the R is 2 to the C. So this would be the largest possible dimension of a vector space of function of this type. And certainly, if we assume the generalized continuum hypothesis, we would have that there exists a 2 to the C vector space of these functions. So then at that point, we wonder, okay, would it be possible to obtain the best possible result, 2 to the C vectors, 2 to the C dimensional vector space of these functions, without having to assume the generalized continuum hypothesis? So in other words, can the 2 to the C linearity of the set be obtained in CFC? Zermelo-Franken and Asimov-Chase, typical setting, where it was proven 3 years later that this is undecidable. So the interesting part is that at that point, almost everything we obtained was always maximal possible dimension in linearity for any property that you can imagine. But at that point, we found an undecidable case ordinality, meaning that you can assume that there exists a 2 to the 3-dimensional vector space of sigmund functions. You add that statement here, and you get no contradiction. Or you assume that not added here and no contradiction. So we have two different models in which that would work, and there are no contradictions. So this is something that to us was surprising, because at that point everything was positive. And now the other way around. Okay, let us talk about a different, within the set of continuous functions again, something that is pathological on the other direction. And I date back to a result from 2005 by Vladimir Gurari and Quarta. If we denote by C wedge the subset of continuous function 0, 1 admitting one and only one absolute maximum, then if we have V, a non-trivial linear space inside this set union 0, then V must be one-dimensional. So we cannot have a two-dimensional vector space inside this set. However, this set is a G delta then subset of this. So containing large vector spaces has nothing to do with being algebraic generic or not being algebraic generic. So you can have a G delta densus set, which is something huge, but that set doesn't even contain a one-dimensional vector space, which intuitively is strange, but anything can happen. But what about if we move to the set of continuous function attaining the maximum only once, but in R? You have compact set. What about R? How that can be? Well, in 2005, the same author, Vladimir Gurari and Quarta, proved that this set is two-lineable, meaning that inside the set of continuous functions admitting one and only one absolute maximum in R, together with 0, we can have inside a two-dimensional vector space. The proof was given constructively. They gave the basis, the two functions, and proved that the linear span of the function beyond the set, okay? So we have Vladimir. So what about larger? Can we have like a three-dimensional vector space inside the continuous function in R admitting maximum only once? Can we have it? Well, this problem was open for 16, 17 years. Many attempts were given, many partial results were given. At times, some people thought that yes, and tried to produce the vector space. Some people didn't succeed. I mean, many people, no one succeeded actually, because the answer is no. It was shown in a joint work with Bernard Cabana and Gustavo just 2.5 years ago or so. And the proof, far from being close to real analysis techniques, involve algebraic geometry, Moore's theorem, and it was a lot of topology involved. So the technique is usually, it didn't really give you the hint that really was in that direction. So this would be like a almost non-linear set, but it's funny that it contains a two-dimensional, but not a three-dimensional. And after introducing the topic, let us go to the joint work with Per. Okay, we're again in the setting of continuous function and the compact 0, 1. And we define a concept called annuling function, which is very simple. A function f is said to be annuling if it has infinitely many zeros in 0, 1. It is easy to construct, let us say, I say here, C-generated algebra of annuling functions in C0, 1. I mean, it is easy because you can just take, for example, in 0, 1, something like x squared times the sine of 1 over x to the p, with p bigger than 1. That has infinitely many zeros in C0, 1, and you can show that they are linearly independent, and so on. And to prove, it's not hard, it's just to do some calculations. Okay, you can actually know what the basis would be, take the span, or even you can multiply them, and the product of 2 of them is also in the span, and so, and is not complicated. But the question that we're interested in is about finding a closed subspace of annulling functions in here. Okay. Moreover, a closed infinite-dimensional closed subspace of binary space in here, where that has every function has infinitely many zeros, but also on the same points, the zeros, which is to ask much more, to control where the zeros are. And then in 2014, in a joint work with Per and Vladimir, we show the following, that if we have X any infinite dimensional closed subspace of C01, that exists first an infinite dimensional closed subspace Y of X, and a sequence T sub K of elements of 0,1, pairwise different elements, such that every function in Y is 0 exactly here. We will solve the question, but I mean, the result itself deals with spatiality, ability questions that were coined by Burari and Richard Aron in earlier works. But in this paper, the techniques that were used were related to something else. That's what I'm going to talk about very briefly. Some consequences of the previous result were the following. Let us give a definition that we are all familiar with, but just to recall them. Let us denote by O sub alpha beta of X the oscillation of a function X in 0,1 of alpha beta, as we all know. And now, if we have any positive number and any element is 0 and 0,1, we see that this element T0 is A oscillating for a family of function F if for every D bigger than 0, there is X in F, verifying this. Great definition. And then for short, we will just say that T0 is oscillating if it is A oscillating for some A. With this notion at hand, and the set of oscillating points of a given family of functions will be called the oscillating spectrum of the family. Okay, you get all the oscillating points of a given family of functions. We call it the oscillating spectrum, denoted by omega f or omega af respectively, depending if we're talking just of oscillating point of A oscillating points to be more precise. And some results that we obtained that were needed in order to achieve the spatiality result, even though it doesn't seem to be intuitive beforehand, are the following. That are related to this notion of oscillating spectrum, that a uniformly bounded set F of continuous function is compact if and only if the oscillating spectrum is the empty set. Also, if we have X as subspace of continuous function, 0,1, if omega X is finite, then X is isomorphic to the subspace of C0. More properties that this enjoys. For any closed subset M of the intervals closed compact interval 0,1, there is always a subspace X of C01, so that N is equal to omega of X. Another property, there exists a subspace X of C01 for which omega of X is not compact, it's not a complex set. So trying to cover all possibilities that may happen with this oscillating spectrum notion. After this result, the paper, because it was focused on spatiality, it was just used as a tool, was left with several open questions at the end. After one, you say, okay, we have X at space 0,1. If omega is finite, then X is isomorphic on some space of C0. We just mentioned that. But what if the oscillating spectrum is countable? What would happen then? Second question, if we have X, Y subspaces of C01, how must omega of X and omega of Y be in order to make X and Y non-isomorphic? Another question, open question. Another one. Which conditions sum a subset of 0, 1 shall guarantee that n equal to the Euclidean spectrum of X for some subspace X of 0, 1? And a last question. What are the properties that omega of X should enjoy in order to obtain that X is uncomplemented in C0? And this is a question where we thought about, not much, because our aim was a different one, but we thought they were interesting. And just a few months ago, in just this year, in Journal of Functional Analysis, Roisier showed that first, N is a F sigma set if and only if there exists a subspace X, C01, such that N is equal to the oscillating spectrum of X. And for any F sigma set M, there exists a complemented subspace F of C01 such that omega of X is M. Answering Q3 in whole and providing some infant directions toward Q4, which deals that the goal of this is to somehow show that even though Per, as Gustavo said earlier, solving the invariant space problem for binary space in the 80s, the techniques that he developed gave birth to many other works related to it, as some of the work that Gustavo presented today. And in this linearity spatiality work that we did 9 years ago, the techniques that Per developed there help even nowadays to keep working on binary space theory, which is a recent paper in the Journal of Functional Analysis, beside our paper from some time ago. So just to finish, to mention that I don't have many photos of Per, but I've been going through my hard drive looking for many, and no matter how many photos I find of him, he's always smiling all the time. But the only one I found in which he's not really smiling that much, but he's still smiling, is one that of a lecture that he gave in PASEC in 1995 that he didn't have because it's a photo of a photo. So this is the end of my talk. Thanks for your attention. Thank you, everyone.
Thank you, Juan, for your talk, so full of surprising results. Any question or remark for people present in the room? Any question or remark for people? No question. Online? Well, if not, we thanks again. Okay, please, people online will know that next talk by Professor Perenflo will be done fully on the blackboard, and then the problem with the reflection of the light hopefully won't appear. 7 minutes.
Muy bien, Juan, todo ha hecho muy bien. Los dos, de hecho, yo quería hacer un poco más. No.
Yo creo que la condición y probamos que no hay contradicción usando números de Cohen, un año estudiando eso. Podemos hacer eso. Pero hay una clásica. Todo lógica. Pues números de Cohen, Orpin y cardinal. Pero no es un tema de estilo, porque llevamos 2 años casi para probarlo y sacamos.
Se va a quedar en el
Yo sí que tenía cuestiones. La primera era más fácil. Si yo cojo todos estos es que no quería cojo todas las cosas. ¿A qué horas?
Sí, pero no es cerrar. Claro, lo que yo creo que es fácil. No,
seguro que no es fácil.
Sí, yo creo que no. Yo creo que de todas formas lo que no fíjate es, dado cualquier espacio de bala, yo creo que es.
No,
Pero sí. Y también, puedes ahí controlar los ceros, a lo mejor te salen más.
Sí, pero es una música ahora, y no solo
Vale. No, pero pero como se comprenda. Sí, para ver cómo la base, cómo varía, para verlo. Eso es, la idea es esa. Se usa X elevado a N en un rango de X a la P. O algo así. N mayor de no sé qué, se pegas todo, queda ahí. Bueno, ¿qué tal?
Una pregunta que las dos queda un pelín fuera de la charla, pero digamos que se demuestra que
Eso es lo que yo estaba.
Pues mira, 2 años estudiando forcing, números de Cohen y resultados de cosas. Es muy desagradecido porque te lleva mucho tiempo estudiando cosas raras y en España no hay mucha tradición de esto, de a buscar papers para gente que te oriente y tal, y pues diría que la única
tenemos muy poco cierto continuo, vamos a significar eso de no, bueno, en general tenemos
sí, es verdad. Sí. Efectivamente, de hecho, con uno de los que yo trabajo es el que me obliga a 2 días de esto, de otro, de esto, trabajando. Yo no me encuentro. No, pero yo de hecho el hecho de trabajar en cosas de sentimiento no lo puedo presentar en ningún lado porque y es eso por buscar algo de identidad. No solo que se han hecho
es un reloj, lo encaras, le pones la época del año y por el algoritmo ese pequeñito que marca la hora.
Si lo quiero muy rápido ya es una idea.
Y si no funciona, tienes el móvil.
Claro. Pero no también pues aquí tienes que abrir un SD la parte de abajo. Está muy desesperado. Lo sacas de lo tienes no, lo sacas yo si la gente
El siguiente paso es que la restricción
Okay. So,
Ese es uno de los
well, to me, it's an undeserved honor to introduce Professor Perenflo from Kent State University to the big conference of today, which is the solution of the invariant problem for Hilbert spaces. Once, when you make an introduction in a situation like that, you want to speak forever, and I will try not to do. And then I will say something. Everybody knows solve several key problems in Banach spaces. The separable Banach spaces without approximation property, and as a consequence, the separable Banach spaces without a basis, the Mazur problem, the Woods problem that he got really a live Woods. Did you eat the Woods or not?
Yes, I got this question actually many times, and I had to make a very fast decision, and I'm not sure that I will make the same decision today. But there was a goose dinner arranged with a goose.
Good.
Because I was also leaving Warsaw the next day, and as this was pointed out in a paper, to bring the goose out of Poland would probably be more difficult to solve the approximation problem.
And one must understand that at that time in the communist country, a goose was really a treat, a special treat, because of the food. Well, apart from that, of course, there are far more spaces, like one of the long-standing problems that Gustavo said, that he said it was solved in 1987, and it was actually solved in 1980, if you read this paper. What I try to say that Enflo, Juan Sioane, and Moslerian, the chief editor of Banach Journal, produced a beautiful paper, A History of Solving Famous Problems in Mathematical Analysis, which I suggest to everybody to read, and then I'll stop, in which is that you will read what I have said very fast, but you will read the insight Professor Enflo had for solving, particularly the approximation problem. I have enjoyed solving it. I didn't know it. I should have known. I have forgotten because one of the co-authors is my friend, Juan, but I didn't know. I found by luck, and then I suggest to everybody to read, and I think everybody here will enjoy a lot with that. And also now, if we go to the problem today, which is showing that any Hilbert space and any operator from the Hilbert space into itself has an invariant subspace. And one important thing has to be said is that there is an archive, there is a preprint, which is actually a first draft, and that you have been working a lot to fill.
Yes, there's a second version coming, and it's actually close to the end now, but it's long, much longer, and it has taken time to work out all details correctly. So I'm a little sorry that it has taken so long time. I was hoping to have it ready by now, but there are a few pages still missing from the second version, which I hope will be understood much better than the first version.
Then this is the moment. Professor Enflo, please.
Yes. Thank you for this kind, nice introduction. And I should also thank, first I will just thank Johan for starting to arrange this and for inviting me. And I would also like to thank all other organizers, but there are so many to thank that I will not mention any name. Nobody mentioned and nobody forgotten. So today I will sketch an outline of a solution of the invariant subspace problem for Hilbert space, showing that every operator on Hilbert space has a closed non-trivial invariant subspace. And in more precisely, this is the theorem. I want to show a sketch of the proof. because it divides up the operators on Hilbert space in two different categories or two different sets. And one is what most operators have. Either we have a y so that all the orbit of y under T is orthogonal to an element x0 minus y for all j bigger than or equal to 1. That means that Ty prime is an invariant subspace because we'll never be able to get to x0 if we keep iterating. Ty prime. That's one possibility. The other possibility is something that is similar to the invariant subspaces for shifts, namely that we have a y prime, and if we iterate y prime under T, we'll just get elements which are orthogonal to y prime. So, of course, this iterates. They will not be they will not be what we call cyclic. A cyclic vector is a vector where the orbit, the closed linear span of the orbit is the whole space. So there are these two possibilities of invariant subspaces that I will talk about. The approach to do this is what I was thinking, and this is from the 90s. There's a joint paper with me and Shamim Ansari where we prove that Victor Lomonosov's famous theorem on operators commuting with compact can in Hilbert space be given another proof, another short proof also, and using what we call extremal vectors. And so now I'll pass to the next picture. We have an x0 in Hilbert space, and we have a y prime, which is it has a positive scalar product. It could be quite modest with x0. And what we do is we try to find the best LT. LT is like a polynomial on an analytic expression in T, so that LT y prime gets within a certain distance to x0 that we have prescribed here. We call it epsilon, and epsilon is between 0 and 1. So it's in line with this picture that I have here. And what is important here is that we want to find the best L, the L with the weakest 2 norm. So we put LT is equal to summation AJ TJ, and the norm of L, we take just the sum of the squares of the coefficients to get the norm of L squared. This norm can seem to be a little bit unusual or unnatural for an operator, because usually we talk about operator norms or so. This norm does not have too much to do. It has a little bit to do with the operator norm, but it's really quite different. And after having tried many other norms, it turned out to be this one, for reasons that I'm not really sure about, were much better than any of the other norms. Now, if we have a minimal L, then we know that if R is orthogonal to L, that means R is this. And summation Rj, Lj. Well, we can use complex coefficients or real coefficients. Let's say that this R is orthogonal to L. Then the minimality of S implies that RT applied to the vector y prime when we scalar multiply that with this vector x0 minus LTY, we get 0. That's just like at a minimal point or maximum point, the derivative is 0. That's nothing more than that. But from this we can draw an important consequences. This implies that for every j bigger than or equal to 1, then tj, the scalar product between tj and y and x0 minus the scalar product of this is smaller than or equal to, and I will give a name to this scalar product. I will call this epsilon theta. Epsilon refers to the distance, and angle is how much this differs from the right angle. That's why we have this notion. But because of the minimality of L, if we take this scalar product, it will be smaller than or equal to tj to this epsilon theta, and that's because of this. If we expand tj, we can write it as a times lt plus rt. Here r is orthogonal to L, and if we take the scalar multiply this with x0 minus lt y prime, we see that we get just a times epsilon theta. What's good about this is that if we are looking for, let's say, almost invariant subspaces where we are here close to right angle, it's enough to look at just LT or y prime, because if that has almost the right angle, we know that the orbit of y under t will be as orthogonal to x to this vector here. So here we could, or if we want, we could introduce a concept, talk about almost non-cyclic vectors, y prime vectors, where an LTY prime produces an angle here which is close to the right angle, and where the orbit is almost orthogonal to x0 minus LTY prime. So that's why it's useful to use this best way to get within epsilon from x0 with the vector y prime, to move it in the most efficient way. Now, this is what this method, the main construction in this paper, is doing. It's we are going to produce a sequence of y primes so that we get closer and closer to right angle here. And if we manage to get such a sequence to converge, we have an invariant subspace. Because if it converges, if this LTY prime converges to something which is orthogonal to this vector, we will have an invariant subspace. So this is what I tried as a main approach already from more than 20 years ago. What I knew already then, and which turned out to be very important, that this thing cannot always work. Because there are cases of invariant subspaces where we cannot do this approximation. Any sequence of this type where the epsilon theta gets smaller and smaller, it will not converge. So how do we recognize that the method doesn't produce this type of situation? And so just to tell about one thing, I'll describe that this doesn't work for certain shift operators. But what made me convinced about 1 year ago that this approach could work to solve the invariant subspace problem was the following. I have a main construction which produces smaller and smaller epsilon thetas, and if it doesn't break down, it goes down all the way to epsilon theta to 0 and converges, then we have found an invariant subspace. But what I found out about 1 year ago is that if we do my construction of better and better epsilon thetas, and the construction breaks down, then we have this situation. So then we have this type of construction works essentially for all cases. If it doesn't work, it must be something like a shift. And that discovery 1 year ago made me believe that this must be the right approach, and probably one can work out the rest. Okay. Let me show you how this approach with smaller and smaller epsilon, how that cannot work for certain weighted shifts. Let me take this example. I don't even write it down, but En is just the standard orthonormal basis of Hilbert space, E1, E2, etc. And if we just take a weighted shift like this, try to move in 0 plus epsilon n within let's say 1/10 of x0. What I'm saying is that this is very, very hard, because if we take LT is equal to A0 identity plus A1 T1 A1 sorry. We take such an L and apply it to. We can let it continue. Apply this to E0 plus En. If we want this to be within this distance to x0, we must have a0 be at least 9/10, because this term here is the only one that contributes to E0. All the others will, and when we have used A0 is 9/10 or something like that, then we have to get rid of the En. And to get to the EU, we have to repeat T to the J many times before we have anything that it has any effect on En. I mean, Tj E0 plus En. It doesn't have any effect on En except for J is equal to N. And that effect is extremely small because of the weights. It's going to zero. That should go to zero fast. So this is an example. To move this within distance 1/10, we have to use an enormously big L2 norm on the LT. We have to use 1/, and here the AN term has to be enormous to have any effect on En. So that means that here we have in our cells E0 plus En is an almost non-cyclic vector. But it's not going to be close to a non-cyclic vector, to precisely non-cyclic vector, because if we have these weights going fast enough to zero, then let me write it here. Any vector, it's a known result from operator theory and summation alpha I EI with alpha 0 different from 0 is cyclic. So anything that has any E0 term is going to be cyclic if the weights go down sufficiently fast to 0. That's a known result from operator theory. So in this case, obviously we cannot approximate a non-cyclic vector, but we cannot, by what we get here, we get E0 plus En is almost non-cyclic. But in order to be cyclic, we have to get rid of E0. In order for something to be non-cyclic, we have to get rid of E0. And since we are going to move it close to x0, the coefficient in front of this is at least 9/10. So this shows that a method that tries to approximate a non-cyclic vector by almost non-symmetric vector cannot work. So that's why this discovery that the method of approximation to get smaller and smaller epsilons, it breaks down for shifts. That is what made me so convinced. And it just, if it breaks down, it is essentially a shift. That made me convinced that this is a good approach. Okay, let me now tell let me now say something about all the technical problems that we meet when we try to do this. We are trying to construct, we have here an y prime. How can we from y prime construct a better y so that we get closer to a right angle here? That is what the main construction does. And it's actually not hard to see if one looks at the paper and the construction that if we have a certain y prime and we get here, we can always get something better. We can always get a smaller epsilon theta. But all the estimates that we need uniform estimates to have the procedure converge. And that is what really is the big problem at this point, to get these uniform estimates. And I'll just say some things about what we get into when we try to do that. This is a way to represent the best L by just using, just basically using that if something is orthogonal to it, P of that thing is orthogonal to this. So let me give this representation. Put first, first let me define this operator dy star x. It's xy times the identity plus x plus this expression. So it's an operator. Here I should mention also that in order to make things converge in a nice way, we will actually assume that the operator norm of t is small, and it doesn't matter. We can always do that without any loss of generality, because if we have an operator t, t, if we multiply that by some number, mu, this mu times t, it has the same invariant subspaces as t. Doesn't change anything. And we can also add a multiple of the identity. So we can always, if we want to work with an operator t, we can always modify it to a scalar times t and plus a scalar times the identity operator. It doesn't change invariant subspaces, they are the same. So what we'll do here at an early stage, when we work with complex scalars, basically we can work with either complex or real scalars for this thing here, but if we work with complex scalars, we know that the spectrum is non-empty. So by adding a suitable lambda to T, we can always say that we can assume that 0 is in the spectrum of T, so that so we can assume by looking at this that T has small norm and it's not invertible. And that is actually something that we are going to use. Some other things that we are going to use later on is that the x0 that we have chosen is not in the range of T, and that the y, starting y, is in the range of T. There are other ways to put this, but this is actually, if we look at this thing here, x0 minus, if this is not in the range of T, and y prime is in the range of T, we see that this cannot be 0, and it's actually, we are going to use that if y is in the range of T, it's harder to move it close to x0. But this is just a technicality. We could put in other things. We could put in other things than these to achieve the same thing. Okay, so here is the operator y, v y star x, and I'll put in another operator, which I call Vy of L, and L is a polynomial, so that is, or an analytic expression, so that's equal to LTY. These two things. With these two things, I can describe or represent the L's which have a minimal norm in a way that is where I can actually start to apply harmonic analysis, which is an important tool for having this whole procedure work. So LT of y prime, it's actually equal to something where I use this type of notation, and let me tell you what it is equal to. It's equal to Vy, V star y, of this expression. Okay, this I'm not going to go through the computation to do this, but that type of representation was already in the paper with me and Shamil Mansari, actually from 1998. So now, if we want to achieve the distance epsilon to x0, we can choose the best LT to get the distance 0. But then it turns out, in order to have this, we have to use much bigger y here than here. So y is just a multiple. I don't know what I put in. Let's be calling p times y prime. That has no less than 1, but this y will actually, in the paper, more or less have the norm 1 over square root of epsilon theta. Those computations are not hard, but it takes a little bit tedious to go through them, but they are already in the archive version, the first version. So this is the expression that we are going to work with, because we form a sequence yn. This is the sequence that's going to get closer and closer to a non-cyclic vector when we have normalized it by yn plus 1 is equal to yn plus summation rj tj yn. So when we do this, we can change this y to an expression like this, and we can just plug that in here, and we can see how nty prime changes. It's just a formula. We get the formula for and how do we do that? Well, this is an invertible operator. I should have said this, which I forgot to do, that dy this operator is compact, self-adjoint. And it has a convergent sum of eigenvalues also. Sum of the eigenvalues is actually equal to summation of is actually equal to this of eigenvalues of this operator is equal to this thing here. That's also not hard to prove. We can do it by approximation by finite dimensional operators. We can approximate this by cutting the expression off at the end and then let it go to infinity. And this formula is immediately for if we cut it off at finite place, because it just uses that the trace of an operator is invariant in basis. Well, yes, this formula. Of course, it's when I just talk about it first here, it's impossible to see that, but it's easy, and well, I think it may not actually be in the first version of the paper, this formula either. But so this operator here is invertible, and we can just use the formula that if we have an invertible operator A and we add a small operator B and take its inverse, we can expand that. That's inverse minus A inverse B inverse of A plus next time we get. This formula is just what we use here, where we change yn to yn plus 1, and we use this formula. We can just use this formula here, and we can get the first order change of. We get the first order change of where we get when we have modified y prime. And then what we do is, since we have given it this form, it turns out that the changes we get, they can be described in elementary Fourier analysis, which is kind of nice. That's because of the particular form that we have moved from yn to yn plus 1. I should here squeeze in just a remark. This seems to be a little bit specialized place to go from yn to yn plus 1. We have just had some kind of analytic expression in T applied to yn. I tried for many years to do the general move from yn to yn plus 1. We just put yn plus 1 is equal to yn plus z, and we let z be anything in the Hilbert space. But it turns out that then we don't get any nice formulas, and we get into difficult problems about the relationship between T, the adjoint of T and T. I think there are quite a few interesting problems about this connection, which comes out of this failed attempt. But after some years, it turned out that if we apply this formula, we can use elementary Fourier analysis to see where LTY prime, where it goes after we had made change yn to yn plus 1. And what we do is we want it to move closer to a right angle, so we want it to move so that this angle here gets closer to 90 degrees. And we can do that in several different ways. We can require that the distance to x0 is constant and move it along here, along this line. And then we see that the angle gets closer to the right angle. What I've done in the paper is actually to keep the scalar product of this with x0 constant. So we require that we move, by moving from yn to yn plus 1, we require the x scalar product with x0 to be constant, and we require the distance to increase, the distance to x0, because if we take this, we are closer to the right angle here. Now, if this could just be, as I said, because we are just working with a few vectors in Hilbert space, and it's actually easy to show that they are not linearly dependent. So that means that if we have a certain epsilon theta, a certain angle, and we want to get it closer to 0, we can always do that. We can always get a better point than LTY prime. But the difficulty is that we need things to converge. We need uniform estimates, and that is what makes this hard. Because if we manage to get certain estimates for yn, we need to have as good estimate for yn plus 1 also, although we have messed up yn plus 1 with this expression here. And that, so that is what most of the later proportion of the paper is concerned with, showing that we can do this in a uniform way. Now, I see your time is not quite running out yet, but I will mention one other lemma, which I've used many times to get this type of uniformity, and which is also not in the paper because I only realized that was a very convenient way to get uniformity, the type of uniformity I needed. And here I should squeeze in a general remark. After this discovery that either we can use the main construction or we have a shift, to go from there to an end there are many different paths that one could try. And I've tried many paths. And so the one I finally ended up with is the one that I found most convenient, but it's by no means the only way. It's by no means the only one. But let me give, with the path that I've chosen, let me give you one lemma, which I think is, which was a nice surprise in itself that it worked, and which makes computations be much simpler than otherwise. And this is this thing. Consider the eigenvectors of this operator dy. But don't take the operator t now, but we take with at or lambda, what mu t, since that's what I put with operator mu t instead of t. And then the eigenvectors let me call them normalized eigenvectors. Will converge to the so normalized Gram-Schmidt expansion of y dy as mu tends to 0. this is actually turns out to be very efficient to compute because Gram-Schmidt expansion, Gram-Schmidt expansion is easy to compute with, much easier than many other things in any case. So maybe that was really most of the things I wanted to say about the general method to construct a sequence according to a particular formula, yn plus 1, and in that get more and more non-cyclic vectors, and also to at least mention a few of the tools to be able to do this in a converging way. But I think I should as well leave the last minutes for questions. To go through more details, it's kind of useless. I mean, if you have a week, I would be glad to go over the whole thing. And it should be enough to do it. A week should be enough to do it, but not 1 hour.
Thank you. Any questions, Mark? Any question? I have a very single one. How do you go from here to obtain the subspace? And how big is the dimension of the subspace, the invariant subspace?
Okay, the invariant subspace is an orbit in every case.
Yes.
Described here, it's the invariant subspace is Ty prime, this both T1 prime, T square prime, Y prime, etc. And since we have this scalar product all the time, it's invariant under T. So that's the invariant subspace in this case. In this case, it's the element Ty prime, because the whole orbit Ty prime, T square Y prime is orthogonal to Y prime.
Oh,
so that's also invariant, yeah. So that's, but in all this construction, it's a whole orbit that we get as an invariant subspace, yes.
And in general, I mean, if the dimension of the space is finite, can be finite, but in infinite dimensional Hilbert spaces, how big can you get big?
Well, we
subspaces, big invariant subspaces?
Okay, essentially, this x0 we can choose in any way. We should do this, but of course, this is theirs. So, and as soon as we have chosen, we just can start. Okay. We have chosen x0 here. We could start anywhere where we have a positive scalar product with x0. We can start y and do this construction, and it should end up with an invariant subspace, either shift-like or we end up here somewhere and the whole orbit is orthogonal to this element.
But in some cases, the subspace could have dimension 1 if it's.
Yes, this I should mention also. When this looks like a constructive proof what I've done here, but all not on every line, but on every page many times we arrive at some vector and we assume that it is cyclic. Otherwise we could finish.
Yes.
So we have very much of this type of argument. So in that sense, it's not really totally constructive.
Yes.
We all know we can use this type of argument.
Any other question? If it's not the case, we can from here. No, I have actually 1 moment ago. This is and look, so I understand each other with that. Are there somebody? Well, my gosh. Okay.
I'm not waiting for a question.
He said, yes, please, I have a one question.
Thank you very much. Somebody is writing.
Yeah.
Is there any?
Is there any?
We are waiting for a second. Is there any size for the set of this kind of operators?
This is for every operator on the it should be non-zero. And it should have, without loss of generality, we have assumed that the operator norm is small because if we have T, we can always get the same invariant subspaces mu T plus lambda times the identity. So, but other than that, it should cover all operators on the space. Yes.
Felix. Your brother, Javier.
One question. Almost everything you do here is related to Hilbert spaces because you are taking more orthogonal vectors in this.
Yes, exactly. It's already.
The thing is, I think this should work, or at least this should be also true in many reflexive space.
Yes, this is what I feel hopeful that this general approach can also be used in uniformly convex spaces or so on. I mean, we have weaker concepts of orthogonality and so on, and I haven't really tried to penetrate how that works. But anyhow, in all the constructions of counterexamples in Banach spaces, in my original example, I state even on the first page that it uses so much, the construction for a counterexample uses so much that it has little L1 and is very non-reflexive, so that construction gives our weak support that the answer in Hilbert space would be like this. So, of course, if one takes the paper by Shami Mansari and myself, we use the external vectors in a little bit, or quite a bit different ways. We take a non-invertible element, x0, say, it's not in the range of T, and then we try to find the smallest y so that T and y is near to x. So we try to find the best approximate inverse, and we work with that instead. And that has many similarities with this type of thing, but here we work with the best operator to move something to. We fix the element and we use different operators. There we fix the operator and use different elements. But there's some difference in how things come out, because what we get in the Shami Ansari paper, we get hyperinvariant subspaces, so that we do not only get invariant subspaces which are invariant for T, but also for operators commuting with T. This we do not get in this other case. Of course, I tried both these things to do approximations. In this case, I approximate y by, in the other case, I approximate the operator T to the n and said, let's not just work with the operator T to the n, let's say T to the n times something or whatever. And it turned out that one gets much better handle of things and so on, which one, if one does it this way, one fixes the element and works with the operator instead. So although I for a few years actually tried the other way, I wasn't successful in getting close to anything that I was optimistic about.
Any other questions, remark? Well, what we can say now. If this is a mini workshop, I would like to say that I feel like Pedro Piqueras in the Telediario, okay? That the real organizer has been Juan and Domingo and I think we should thank them. Which questions are available for everybody if you want? Everyone?